Okay, so the plan for today is to just continue on with chapter 4. And if we finish up chapter 4 today, then start on chapter 5, discrete probability distributions. Continuing on with this idea of probability. Sorry, my allergies this morning have just been absolutely crazy with this rain over the weekend. So, um, note that I did update the Unit 1 exam grades last night. So if you haven't already, check your grades on my stat lab and you should see an updated grade. Most folks got, an extra couple points or so for partial credit. Some folks, particularly if you got a higher grade, you might not have gotten any extra credit points because, there just maybe wasn't, I shouldn't say extra credit, partial credit. If you got a higher grade, it's a little less likely that you get partial credit because you had, fewer things wrong to get partial credit on. Um, so you might not see an updated grade, but most folks got a few extra points here or there for partial credit. Note that midterm course grades are due this week. So I'll have midterm course grades in. I think I've mentioned this before in this course when we talked about weighted averages. Um, I wouldn't look at a midterm course grade as being a super granular representation of where you're at in the course. So I have to give you a grade A, B, C, D, F, and that's supposed to be somehow some sense of an estimate of how well you're doing in the course at that time. But of course, that's not really a well-defined problem. So what I would say is when you look at midterm course grades, you know, if you thought you were failing the course, but you see that you have a B or an A on midterm course grades, well, maybe then adjust your expectations, right? Say, oh, okay, how I thought I was doing in the course is maybe inconsistent with how I'm actually doing in the course. Maybe I'm doing better than I expected. And if the opposite's true, if you thought you were doing well in the course and you see a D or an F, then again, something may have gone wrong somewhere. You might need to look into that, see how you could remedy that, what should you work on in the future? If you think that you're about working at about a B level and you see a C on the midterm course grade or vice versa, again, it's not really meant to be that granular of an assessment of a metric. And again, part of that is like, okay, how do I decide, you know, how to weight the homework you've completed already, the unit 1 exam, like should I pretend that your unit 2 exam is going to be the same score as your unit 1 exam? Like there are pluses and minuses to that. Should I, underweight your homework weighting in the course grade weighted average because you've only completed like half or so of the homework in the course so far, but you've completed like say the entire unit 1 exam at this point, right? So don't take these take these midterm course grades with a grain of salt. And I think that's probably a fair thing to say in any course, right? The final course grade is very well defined. This is how it's computed. Midterm course grade is supposed to be an estimate of what your final course grade would be if you continue working similarly for the rest of the course. But that comes with a lot of caveats. And then one last note. So we just finished up the Unit 1 exam. We did not use proctoring on that. Um, you know, as I mentioned, we were having some challenges with the ProctorU system. I met with our CCAC's lead guy for the ProctorU collaboration. And long story short, it seems like solving the tech challenges are going to be at the very least much more challenging than we had expected. So we will be using Examity. We maintained access to Examity through this semester. It would be really nice if we could just keep that going, but I think our folks are working with ProctorU to kind of get some of these tech challenges sorted out. And I think a lot of other colleges are having a similar problem. Basically, Examity is, in the near future, they're looking to phase it out and they're looking to replace it with ProctorU. And it seems like that transition is not going too smoothly. So we are sticking with Examity, the kind of tried and true system for this semester. So that was very good news to me. If anybody has used Examity in the past, I use the automated um, set up so there's not a live proctor. Um, so it's very it's very robust. It's not when you have the live proctors in play, there's a lot of things that have to work just right for everything to work smoothly for your exam. And I think that's just a little too much to ask. Um, you're already taking an exam, it's already a little stressful, and then to throw that on top of it isn't reasonable. So I use the automated proctoring option on Examity. And in the near future, most likely today or tomorrow, I'll post an Examity practice exam on my stat lab. The only purpose of this practice exam is for you to practice the Examity system. So for you to go in and like get your account and your profile and all that set up on Examity if you don't have it set up already. Uh, for you to go through the Examity like setup process, make sure that it works with your browser that you're using, with your computer and all of that, to like get into the exam to see what the experience is like. The exam just has, a few dummy questions in it. It is timed, but again, um, it's just meant to practice the Examity process. So, I didn't take a lot of care in making sure that it was reasonable to complete the problems in the allotted time or whatever. It's just meant so that you have something to do in the exam. You can type stuff out or enter answers and then close out the exam, close out the Examity session, and make sure everything works for you. So keep an eye out for that in the next couple of days. And I'll post an announcement on Blackboard to be sent to your emails as well when that is up. So we will use that for the rest of the exams in the course. So make sure you do complete that and complete it sooner rather than later. And that way, if you do have a tech issue on your side or with Examity, but Examity is pretty tried and true. But if your computer isn't working with it properly or your browser isn't working with Examity properly, it's better to get that figured out early and then and get that solved well in advance of the Unit 2 exam. You don't want to be sitting there, the day before Unit 2 exam week starts up and realize that there's a problem with the uh, Examity system working with your computer and try to get that resolved. Or even worse, you don't want to be at the end of the Unit 2 exam window and realize that. So yeah, keep an eye out for that. So sorry for the hassle with switching to ProctorU and then deciding to not go with that and the tech issues, but that's one of the challenges that we have in the remote environment is, this tech, when it works great, it's wonderful. But when it doesn't work great, it can be quite a hassle. So um, okay, so any questions on any of that? I think that was all that I wanted to say. Any questions? Okay, is the grade that shows up on my lab close to what you'll be using for the midterm grade? Um, Probably, yeah. So if your Unit 1 exam grade was fairly close to your average homework grade, then yes. But I think that my stat lab will overweight your Unit 1 exam grade relative to to how I'm going to weight it in the when I compute midterm course grades. Um, so it probably they probably will be uh, a bit different if your Unit 1 exam grade is a bit different than your homework grades. And if your Unit 1 exam grade is a lot different than your homework grades, it could be substantially different. Um, so probably what my stat lab is doing in the computation, I would have to double check. Again, I mean, that this comes with a huge caveat. Don't place too much emphasis on this. So, you know, these little details, they might boost you up or down by say one letter grade. Um, based on how I computed versus how another professor might compute it versus how my stat lab is estimating it, your current, grade in the course. But, plus or minus one letter grade is not meant to be the level of fineness that's really communicated in this metric. But, but so my stat lab will take all of your exams and weight them relative to one another. And then it'll take your homeworks and weight them equally relative to one another. And then it'll combine the two together. So when my stat lab doesn't have a piece of information, like for instance, it doesn't have the unit 2 exam grade or the final exam grade, it just counts that as like 0 points in your favor, but also 0 points that you could have accumulated, right? So it counts it as, in some sense, like a 0 over 0, roughly speaking. Um, so the my stat lab system is basically gonna, in a sense, pretend that your unit 2 exam grade and your final exam grade are the same as your unit 1 exam grade, is the way you can think about it. And it's also going to kind of pretend, in a sense, that the, say, second half of your homework in the course is roughly equivalent to the first half of your homework in the course. Um, so that's the assumption that my stat lab will make. What I'll most likely do is, or well, what I will do is um, take your unit 1 exam grade, take its proportional weight for the overall final course grade. So I forget exactly what the numbers are, but say this unit 1 exam would end up being 10% of your final course grade. It's somewhere in that ballpark. Um, and the homework would end up being 40% of your final course grade. Then homework would count as 4/5 of the weight for your final course grade, for the midterm exam grade. And the unit 1 exam would count as 1/5 in that case. Um, so the weighting is going to be different between the two. Um, but again, there are 1,000 different ways that a person could compute midterm course grades. So, mainly look at this from the perspective of, like, you know, if it's vastly different than what you expect, if it's 3 or 4 letter grades different than what you expect, um, you know, maybe the expectations need to change. Or you could, of course, check with me and just make sure everything is correct. Um, if it's, 1 letter grade different than what you expect or what you see on my stat lab or something, that's probably just due to, you know, different choices in which models we use, right? George Box, all models are wrong, some models are useful. So, um, yeah, and I mean, obviously the best way to, estimate how you're doing in the course is for, I shouldn't say the best way. That's not really an objective statement, but in my opinion, the best way to see how you're doing in the course is to open up an Excel sheet, have a homework grade, have your unit 1, unit 2, final exam grades, figure out what your final course grade would be, and do a scenario analysis, right? So you say, okay, this is what I did get on my unit 1 exam grade. This is what I have in my homework so far. Let's say I feel like I can maintain that homework grade. And I think that, okay, if I can get this grade on the unit 2 exam, what would I need to get on the final exam to get the final course grade I desire? Right. Or maybe I feel like, okay, I didn't do so great on homework for the first half of the course. I can put in a little more effort. I can put in a little more time, boost my homework grade a little bit for the second half of the course. If my homework grade increases to this amount and my unit 2 exam ended up being this, what would I need to get on the final exam to get a certain final course grade? So I think that's probably a more reliable way to estimate your what your final course grade is likely to be, because you know better what those assumptions look like than I do. So, if you look at your next 2 months, do you say, okay, I have some margin that I could spend more time on this course if I wanted to, or are you already, packed in and you see something coming up in the next 2 months that's going to, you know, take even more of your time? So again, yeah, midterm course grades, not super easy to interpret or frankly for me to decide how to calculate. Um, but that's what I do, is I just take the weighted average of what we have at this point, and that's the midterm course grade I give you. And I think it's pretty rare that there are big surprises there, right? You know what you got on the unit 1 exam, you know what you've been getting on the homeworks. It's pretty rare that people are very surprised by their midterm course grade. Okay, give me 1 second and then we will come back to this. Okay, and lastly, so the quote of the day is um from Marcus Aurelius, often abbreviated as just B1, but sometimes that feels like, be one with yourself or something. But it comes from a quote that roughly translated as something like, stop arguing about what it means to be a good man, be one. Marcus Aurelius was a Roman emperor. Um, so obviously, like, main language at the time was Latin. Interestingly, he wrote his meditations and things in Greek, um, because the Greek language is better than Latin. So classics argument there. There's the two factions in the classics departments, the Greek folks and the Latin folks. But yeah, so I think it's comfortable sometimes to sit there and kind of debate amongst your friends, like, oh, well, what would a good person do in this scenario? Or what does it mean to be a good person, or this or that, philosophy or whatever. Um, it's a lot more comfortable to do that than to actually, you know, go out and be a good person, right? Um, most of us have kind of an intuitive idea what it means to be a good person, and it's easier to sit there and debate about it than to take that first step forward. And I think that it applies to a lot of things in life. It's easier to sit there and debate or plan or optimize or whatever it may be, and never actually take that step forward. If you, it's one of those things, like, if you actually want to do something, then just do it. Like, just get started and start putting one foot in front of the other. And um, sometimes you'll make a few missteps that way, but at least you start moving forward a little bit. Okay, so where we left off last time, sorry, we had a lot of administrative stuff to get through this morning. Um, where we left off last time was the multiplication rule for independent events. We said if two events are independent, that is, if the knowledge that one event has occurred does not affect our estimate of the probability of the other one occurring. So, like, picking two cards out of a deck of cards with replacement, I pick a card, look at it, put it back, shuffle the deck, pick a second card. The knowledge that I got a Jack of Hearts on the first draw doesn't affect the likelihood of getting whatever card on the second draw. Or like rolling a die two times or flipping a coin two times and looking at even an event that's something like the number I get on the first roll versus the number I get on the second roll, or the result of the first coin flip and the result of the second coin flip. Those would be independent events. If we have two events that are independent, then the probability of A and B, the probability they both occur, is the product of their probabilities. Probability of A times probability of B. And we worked our way down to this problem. We worked through this problem, so I'm not going to go through it again. But this brought up kind of an interesting question. And we always have some, computer science folks taking this course. And I know there are some computer science, data analytics, IT folks in this course. So I think this is just a fun little kind of diversion problem. It is a math problem, but um, this came from the uh, the phone app, the brilliant.org phone app. Um, I don't do these anymore, but I used to go on and, do a couple of these problems every morning when I wake up, and, just kind of get my brain working. Um, but this is the problem. And this is related to this, pooled samples problem, which we'll see how, I think. But I actually just really like how this problem is set up, because there's kind of a natural solution to this problem. You think, oh, okay, this might work. But then going along that solution actually leads you back. You can kind of circle back and you can see, oh, okay, yeah, there's actually a better solution to this. So I really, really liked how this problem was designed. If we remember the clinical labs problem, the idea was we pull together, let's say, 10 patient samples, and the entire pool tests positive if any of the patients is positive for the disease. If it's a fairly rare disease, say like chance 1 in 1,000, if our pool tests positive, then it's quite likely that only one patient in the pool is positive. It would be much less likely for us to get 2 or 3 patients in the pool that are positive. So most of the time we're doing a search among, let's say, 10 patients pulled together or 100 patients pulled together. We'd be doing a search for one patient. Now we can um, we can just exhaustively search for them. We can just test every patient, then we can say, okay, the pool tested positive. We'll just break it into 100 different tests for each of the different patients, test them all, and get our answer. That's certainly a way to go. And if we had realistic, time constraints or whatever, if we had to get this answer back to the patient or the clinical team pretty quickly, that's probably what most clinical labs would do. But just as kind of a thought experiment, if we were really, really concerned about reagent time and tech time, and we were less concerned about complexity and turnaround time, um, so if we were really concerned about finding that one patient in the minimum number of tests, how could we go about that? And that's where this problem comes in. So the problem statement is that you have 25 coins. There's exactly one fake coin, which is lighter than each of the others. And each of the others, the real coins, have equal weight. Using only a balanced scale, what is the fewest number of weighings you would need to make to ensure that you determine the fake coin? And I think for things like this, where we're looking for an optimization, the fewest number, it's good to just get a number on the board, right? So we have 25 coins here. We have our balance scale. I guess that's not what it looks like. It was like this and then like that. One of these balance scale kind of things. And I mean, we could just put one coin here, put coin number one there, put coin number two here. If they balance, get rid of coin number two. If we put coin number two here and this one's heavier, then coin number one is the lighter one. If I put coin number two there and coin number two is lighter, then coin number two is the one we're looking for, the lighter, the fake one. So we could weigh coin one against coin two. That would be one weighing, and then against coin three, that would be another weighing. So we could do it in 24 weighings, right? We could basically do coin one against coin two, and then if these balanced, then we could do coin one against coin three. If they balance, coin one against coin four. So worst case scenario, the very last coin that we chose to test against coin one, that would be coin 25. That would be the one that's the fake one in the worst case scenario. And we would have done 24 weighings to get there. Can anybody think of a way that we could figure out which one is the fake coin, the light coin, in fewer than 24 weighings? One thing we might realize is that if we know there's exactly one fake coin, if I put one and two on the scale, if it's imbalanced, then I found the fake coin. If it's balanced, then I actually know that neither one nor two are the fake coin. So I could weigh one against two. Kind of best case scenario is that this is imbalanced, and then I found the fake coin right away. Worst case scenario is they tie. And if they tie, if they're balanced, I know neither one is the fake coin. So then I could weigh three against four, five against six, and so on down to 23 against 24. And if all of these balance, then 25 by process of elimination must be the fake coin. So I could have done 12 weighings. But I can actually be a little more efficient about this. Does anybody see a way to make that happen? Particularly any of my computer science folks, is there a search method that might help here? Any thoughts on that? Well, one thing that I might do is say split the coin, say roughly in half. Let's well, let's come over to here and think of it this way, that I could split the coins into say 12 and 12 with one left over. And let me maybe write the one over here with one left over. I put 12 on one side of the balance and 12 on the other side of the balance. If they balance, I found the one. The other one left out is the fake coin, and I'm done. I did it in one way. Worst case scenario would be that one of the 12s is imbalanced. So let's say that maybe this 12 is heavier, so the fake coin is not in there, and this 12 is lighter. So I know that the fake coin is one of these 12, not one of those 12, and not this one. So now I've got to search amongst these 12. Or I could break these into 6 and 6 and do the same thing. Right over here, each weighing just reduced my number of coins still under consideration by 1 or by 2. Now I'm reducing the number of coins under consideration roughly by a factor of 2. I'm dividing in half. So I weigh my 6 against 6, and let's say that maybe this is the heavier one and this is the lighter one, so my fake coin is one of those 6. I break this 6 into 3 and 3. And let's say here, maybe this 3 is heavier and this 3 is lighter, so I know my fake coin is one of those 3. And then here with these 3, what do? Maybe I do something like just 1 and 1 that I balance, and then 1 that I leave off. If the 2 on the balance, if they do balance, then the one I left off is the fake one. And if they don't balance, then the lighter one is the fake one. So at this point, I found the fake one. And it took 1, 2, 3, 4 weighings instead of 24, instead of 12. So I've done it much more efficiently. So this is called a binary search. And this is what we might apply to this problem over here. So we might apply this to this problem over here, binary search. So we might say, okay, the pool tested positive. There are 100 patients in the pool. Again, if I was really concerned about using as little reagents and chemistry and or chemicals and machine time as possible, and I was not concerned about the time it took me to get the answer back to the patient or any of that, or the complexity of the process. So, I mean, this is really very much a thought experiment, not something that would necessarily be practically implemented, but I could say split my pool into 50 and 50, 2 smaller pools of size 50, and test each of those pools. It's going to be very likely that we're just searching for one positive patient, and one of those pools of 50 is going to come back negative, and we'll be able to throw out all of those 50 folks from consideration with just one test instead of having to do 50 tests. And then we'll have narrowed it down to our probably one positive patient is in this 50. We can split that 50 into 25 and 25, search again. The pool that comes up positive, we continue searching there. The one that most likely is going to come up negative, we get rid of that one. We've now eliminated 25 folks with one more test, and so on. So binary search is pretty efficient. We get our solution in logarithmic time, which in computer science terms, that's a very nice thing. It means that as the size of our population scales, the difficulty of the problem doesn't scale as quickly as the size of the population does. But actually, what I liked about this problem is that if we think about it a step further, we get to this last answer and it actually leads us to a better answer. Because we say, wait, I put one on one side, I put one on the other side and left one off. Well, instead of trying to do a binary search, which is a very common computer science technique, I could actually go back up to the beginning and say, well, could I have actually reduced my number under consideration even more after this first step? So could I, so I have 25 coins, instead of doing 12, 12, and 1, could I have done something like maybe like 8, 8, and 9? So in other words, I'll put 2 stacks of 8 on the scales and then leave 9 off. If one of the stacks of 8 is lighter, I know the fake coin is in there. The worst case scenario would be if both of the stacks of 8 balance, and then I know that the stack of 9 coins contains the fake. So the worst case scenario would be that these balance and I knock out both of these, and I know the fake coin is in there. But now I've actually gotten rid of 16 coins instead of just 13 from consideration. These 9 can be broken up into 3 and 3. Let's say we put these on the balance and 3 that we leave off. And let's just say that we balance them and it turns out that these are lighter and these are heavier. So I know that the fake coin is one of these 3. It's not on the other in the other stack on the balance, and it's not in the stack I left off. And then this 3 comes down to 1, 1, 1. Put 2 of them on the balance, leave 1 off. So we can actually do it in 3 weighings. And this would use a ternary search, the same idea as a binary search, except we're really leveraging the fact that we really have 3 groups here. We have the 2 groups that we're weighing and the 1 group that we're leaving off. So in this case, a ternary search actually gets us the answer in 1 fewer weighing. So I thought it was a really cool problem because if you think about it, I think most people would kind of come around um, to the answer, the binary search answer, kind of along the same lines, right? You think, how could I just get an answer? Could I make a slight improvement on that answer? Could I do a little better instead of just weighing 1 against 1? I could weigh a bunch against a bunch, and that kind of leads us to a binary search. And then really leveraging the idea that we're leaving some of them off, and we can actually make use of that as well, that we naturally have 3 groups at each stage brings us to a ternary search. So a little bit of math digression, computer science kind of idea, and something that applies um, to this problem. Okay, question about examity. Will the proctor flag us for using the approved calculator? So the system is automated. It flags people for all kinds of random stuff. So I don't know if it'll flag you for that or not, um, but it doesn't really matter if Examity flags you for something. You just continue taking the exam, and if it's the approved calculator, when I review any of the recordings or any of the flags, then if I see that you're using a calculator, that's perfectly fine. Yeah. Yeah, and the setup for the following exams will be the same as the first one. The stuff you're allowed to use and all that, you'll be allowed to use a formula sheet, scratch paper, calculator, Excel and StatCrunch, all of that. Yeah, that'll all be the same. Okay, so let's move on then. We had this discussion of independent events. We saw when things were independent, the math works out pretty nicely. But of course, things aren't always independent. In fact, a lot of the interesting things that we want to analyze are not independent events. Something as simple as, say, drawing a poker hand or a blackjack hand from a deck of cards is not independent because the first draw that I have, if I got whatever, the King of Hearts, and I keep it in my hand and don't replace it, I can't draw the King of Hearts a second time. So the second draw is dependent on the first. If I've drawn the King of Hearts on the first draw and I want to draw the King of Hearts on the second draw, I now literally can't. If it happened on the first draw, it can't happen on the second draw in that case. There are things that we're not really sure if are dependent or independent. So we probably don't want to assume that they're independent. Say, for instance, IQ and annual salary. You know, there are debates about how tied together those two are. Um, it does seem that there is maybe a little bit of a relationship, but the relationship is very unclear. Or things like age and volatility of investments, where, it might depend on the population being studied. If you look at a particular person, just because they're older doesn't mean they're necessarily going to have less volatile investments. But if you're looking across the whole population, well, older folks tend to have less volatile investments and younger folks tend to have more volatile investments. And that's not just a statement of people's mindset. There are good financial reasons for that as well. So, so these are pairs of events that we would not want to treat as independent, either because, like in the first case, we know that it's not independent, that it is dependent, or maybe the second and third case, we probably suspect that there's a dependency there. That if I know that a person is older, I would suspect the chance that they have high volatility investments is lower. We had a multiplication rule for independent events, but dependent events are not independent. We can't use that simpler multiplication rule. We need to develop a more general multiplication rule, and that requires talking about conditional probability. So there's a lot of like little ingredients that go into building up these rules, the addition rule and the multiplication rule. So ideas of, the conjunction and versus or, the basic idea of probability, mutually exclusive events, independent events, dependent events, and now conditional probability. Okay, so the conditional probability of an event B in relation to an event A, we express it with this notation. The notation looks like probability of B, and then we have a vertical line A. This is not like a divided by line. This is not like probability of like B divided by A or like probability of B divided by probability of A. It's not that. It's not a divided by line. It's a vertical line that is its own notation. And we pronounce it as the word given. So let me point to that line a little better. So when we encounter that vertical line, we say the word given. So we say probability of B given A. Or more verbosely, this is the probability that B occurs given that we know that A has occurred. If A and B are independent, then the probability B occurs given that I know A has occurred. Well, B doesn't care about A. If we're independent, then the likelihood of B occurring, the probability of B is unaffected by the knowledge that A has occurred. So probability of B given A is just probability B in that case, if A and B are independent. But if they're dependent, then the knowledge that A has occurred will affect my probability that B will occur. When two events A and B are dependent, we have a multiplication rule for dependent events, or just the more general multiplication rule. And remember, the multiplication rule for independent events was just probability of A times probability of B, right? What's the change here? Well, we have probability of A. In other words, for both A and B to occur, A has to occur, and that happens with probability of A. And then B has to occur given that A has occurred. So I pick one of them to, I kind of imagine imposing a temporal sequence here and say A comes first, did A occur or not? Well, if A didn't occur, then certainly A and B, that event didn't occur. But if A did occur, that happens with probability of A. And then for A and B to occur, B also must occur in addition to A occurring. So A has occurred with probability of A. And then also B has to occur given that A has occurred. Probability of B given A for that probability. So this condition is the big difference between those two statements, between the multiplication rule for independent events and the multiplication rule for dependent events. Very similar structure, very similar idea. A and B both have to occur. So we end up with a product of probabilities, but one of our probabilities is conditioned on the other event occurring. Sorry.
Bless you.
Thanks. Give me one sec. I even switched allergy meds over the summer. I switched from Allegra to what is it, Zyrtec, and it was working a lot better for a while. And I don't know, maybe I'll have to switch again.
Yeah,
But
that's
anyway,
kind of flaring up lately. So yeah.
Oh yeah. Yeah, and with everybody like cutting grass again and all the leaves falling, like the leaves tend to, throw off my allergies and the rain. And so it was kind of like everything at once this past weekend. So, uh, okay, so the multiplication rule for dependent events, again, it's a pretty similar structure to the multiplication rule for independent events. Main difference being that one of our probabilities has to be conditioned on the other event having occurred. Uh, and side note, there's nothing super special about B being the one conditioned on A. We could just as well have said that we want to condition event A on B occurring. We could have said that just as well, right? Of course, the and conjunction is symmetric. A and B is the same as B and A. So interchanging their roles, which is effectively what we did over here, gives us the same result. Uh, so we could kind of make B the primary event in some sense, like the one that occurs first in our thought process, even if these are events that don't have a natural, time flow to them. We can, in our thought process, say, okay, we're going to check whether B occurred first. Yes, it did. Okay, given that B has occurred, has A occurred as well? So we could choose to check B first and then A, or choose to check A first and then B, but one of them has to get the conditional probability on the other. Okay, so let's take a look at this example. So here we have an example where we run a manufacturing plant producing widgets. The word widget is just like a business term where it's just some item that you're producing, and it's just kind of like mathematicians use the variable X when we don't want to talk about a specific number, and business people use the term widget when they want to talk about some item that's not a specific item. So our manufacturing plant produces widgets. There are 4 machines producing widgets at the same rate. For a properly functioning machine, the probability of producing a bad widget is 4%, right? Even a machine functioning well occasionally makes a bad widget. But one of the machines is malfunctioning and it produces all bad widgets. And we kind of imagine that, maybe we didn't know the machine was malfunctioning for a little while. The widgets come off the 4 machines, they get packaged, they get bundled together, they get shipped out. And now all of the widgets from the different machines and all of the good and bad widgets are kind of like mixed in to one big, shipment on a pallet. We randomly select a widget. What's the overall probability that it's bad? Okay, so we have probability of getting a bad widget when we randomly select one widget from this production factory. Well, let's split up our different ways of getting a bad widget. I could get a bad widget and have it come from a properly functioning machine. I'm going to kind of put that in little parentheses. Maybe I'll put it in like green parentheses. Or, so I could have gotten a bad widget that came from a properly functioning machine. In other words, this widget I'm looking at is one, a bad widget, and two, came from a properly functioning machine. Or it could be a bad widget and come from a malfunctioning machine. So I could look at this other widget and say, yes, it's a bad widget, and yes, it came from that fourth malfunctioning machine. So because I have a bunch of different conjunctions here, I have a couple ands and an or, I put in parentheses to be very clear about what the priority is. So or is kind of the overall operation. This is actually important. I was actually doing some working with some tax documents for my mom, and it had to do with like how pensions are taxed in Pennsylvania, and we were reading through the instructions, and it said like, do such and such thing if A and B or C. And it was like, wait, is that like A and B or C? Or is that like A and B or C? And both ways actually like kind of logically made sense and like reasonably and practically made sense. And so I didn't know. So I actually asked my office mate at the time, who was an accounting professor, and she didn't know either. She's like, I don't know. Like, um, so we brought it to my mom's accountant and we're like, what do you think? And he handled it. So um, accountants are like, the best couple $100s a year you'll ever spend. When you have a job and a career, like, get yourself a good accountant and just bring all your stuff and drop it at their doorstep and say, here, handle this, they take care of it once a year. And, um, but anyway, so yeah, if we have different conjunctions together like this, we need to establish the priority. There is, an order of operations for conjunctions that's, technically exists in mathematics, but um, we want to be clear about exactly what we mean. But here I see my overall operation is or. I also note that these are mutually exclusive. In other words, I can't be looking at a widget that simultaneously came from a properly functioning machine and also came from a malfunctioning machine. It can only have come from one of the machines. So these are mutually exclusive, which means I can use my basic addition rule, my addition rule for mutually exclusive events. So I have probability of bad and properly functioning. In other words, the widget that is both a bad widget and came from a properly functioning machine, plus probability of bad and malfunctioning. In other words, a widget that is both a bad widget and came from the malfunctioning machine. Okay, so now I take, for instance, this first probability, and I look at these two events, that a widget's a bad widget and that a widget came from the properly functioning machine. Are these independent? Whether the widget is good or bad versus whether it came from a properly functioning or malfunctioning machine. Well, no, they're not independent. If I knew that the widget came from a malfunctioning machine, its chance of being bad is much higher, 100%, than if that widget came from a, a properly functioning machine. So these are dependent events. Dependent. They're not independent. And the same with these as well. These are dependent events. So I need to use my conditional probability here. Maybe go to red, maybe. Okay, so I suppose, again, I could imagine, I'm kind of establishing a time sequence here. I'm choosing an event to check first, and then an event to check second that will be the conditional one. Well, do I know the overall number of bad widgets? I suppose if I did, then I could do probability of bad times probability of, say, properly functioning given bad. I guess I could maybe do that. But remember that probability of bad widget is actually what I'm trying to find in the first place. I don't know this. I also don't know from my problem statement, given that I have a bad widget, what's the chance it came from a properly functioning machine? Mathematically, I could break my probability of bad and properly functioning up like this. That's mathematically allowable, but it doesn't mesh with the information I have in the problem statement. So let's break it up the other way. Let's check which machine it came from first. And then check whether it's a bad widget. Do I have this information? Well, yeah, I do. I know that there are 4 machines producing widgets at the same rate. 3 of those machines are properly functioning. One is bad. One is malfunctioning, I mean. So the probability that a randomly selected widget came from a properly functioning machine is 3/4. Do I know the probability of getting a bad widget given that it came from a properly functioning machine? Well, yeah, I know that as well. I'm told that the probability of producing a bad widget on a properly functioning machine is 4%. So this is 4%. And we still have this one to handle. We'll do that in a second, but just finishing this first term. So we'll put a plus there and have a little more to do in a second. But the probability of a randomly selected widget coming from a properly functioning machine is 3/4. We have 4 machines, 3 of them are properly functioning, and they're producing widgets at the same rate, times, given that a widget came from a properly functioning machine, what's the probability it's a bad widget? 4%. One note, as usual, trying to be helpful and make my 4s into 9s. Wish the bank would do that. Look at my bank balance, make a mistake, and turn 4s into 9s for me. Okay, and then the second probability here that came from that original OR statement, well, we want to break that up the same way. We have probability of bad and malfunctioning, or I look at a widget and it's both a bad widget and came off a malfunctioning machine, or the malfunctioning machine, times probability of bad given malfunctioning. Okay, so if I pick a widget at random, what's the probability it came from the malfunctioning machine? 1/4. Again, 1 out of the 4 machines is malfunctioning, and they all produce widgets at the same rate. So 1/4 of our widgets overall come from that machine that's the malfunctioning one. And then times, given a machine is malfunctioning, what's the probability that a widget taken from that machine is bad? Well, that's 100%. So 3/4 of 4%, well, that's just 3%. And 1/4 of 100%, well, that's 25%. So I think overall, the chance of getting a bad widget from a randomly selected widget from this shipment where they're all mixed together from the widgets from the different machines, overall, the chance of getting a bad widget is 28%. Okay. Now we do have this idea of a tree diagram. So in a similar way to how a Venn diagram was a pictorial representation that helped us with OR types of events and the addition rule, a tree diagram sometimes helps us with AND types of events and the multiplication rule. So I kind of start here at the root of the tree, and I'm looking for all of the ways to get bad widgets. I could get widgets off of properly functioning or malfunctioning machines, and off of each of those machines, I could get, in theory, good or bad widgets. Even though my malfunctioning machine never produces good widgets, in theory, that's one of the possible outcomes. The widget could be good or bad, and it could come from a properly functioning or malfunctioning machine. So I'll start by drawing 2 branches of my tree, properly functioning versus malfunctioning machine. The same way that I chose the machine type to be kind of the first event that I check, so to speak. Up here, I chose it for all the reasons I said before. I choose that to be my first event here. I don't want to check good or bad widget first and then check the machine type. I want to check machine type first. And then the properly functioning machine could produce good or bad widgets. And the malfunctioning machine could, at least kind of in theory, produce good or bad widgets, even though it's 100% and 0%. So all the way over here, if we go up, up, that's properly functioning machine and good, or properly functioning machine and bad for up, down. Down, up is malfunctioning machine and good widget, and down, down is malfunctioning and bad. So one thing this helps us do is kind of keep all of our possible events over here sorted out. But the other thing we can do is we can write our probabilities on here. Let me go back a slide. So for instance, we know overall, kind of starting from baseline, the chance that a random widget chosen comes from a properly functioning machine is 3/4 versus 1/4 coming from the malfunctioning machine. And now we have conditional probability. So this is like probability of properly functioning machine. And the probabilities we want to put over here are conditional. So if I go up again, that's given that the widget I've chosen comes from a properly functioning machine, what's the probability it's a good widget? And that's 96%. And given that a widget comes from the properly functioning machine, what's the probability it's a bad widget? 4%. And then for the bottom half of the tree, well, 0% of widgets from the malfunctioning machine are good, and 100% are bad. And now to find my probabilities, I just multiply across. So for instance, for this probability here, probability that a widget came from the malfunctioning machine and is a good widget, I just multiply 1/4 times 0%, just multiplying across the numbers across the path that I need to traverse. And that's 0%, or 1/4 times 100% is 25%. 3/4 times 4% is 3%, and 3/4 times 96%. Well, I know that the overall probability for properly functioning machine is going to be 75 percentage points. I've allocated 3 of those percentage points here. This has got to be 72%. And if you do 3/4 times 96, you should get 72. And now I look at all the different ways I could get a bad widget. 3 and 25. Of course, these are mutually exclusive because my tree branched and went in different directions. So I just add these together. So a tree diagram can be a helpful kind of visual aid for keeping straight all of this algebra and arithmetic and probability and all that up here. So we could do this either way. Okay, a couple more examples. What's the probability of drawing a heart, then a spade from a standard deck of cards? Well, so be a little careful. We have heart, then a spade. So there is an order here that's established um, by the statement of the event. This is a slightly different event than the probability of drawing a heart and a spade on 2 draws. Because I could get heart then spade or spade then heart. So I'd have to consider both of those possibilities. But drawing a heart then a spade, okay, what would my first draw be? Well, to be successful in my first draw, I need to have drawn a heart. All the cards in the deck are equally likely to be drawn. And there are 13 hearts divided by 52 cards in the deck. Okay, that's not bad. But drawing a heart then a spade without replacement, and if I wanted to be really careful here, if this was going to be an exam problem or something, I would be very careful to say, drawing without replacement or something like that. Um, but if I'm drawing without replacement, well, if I'm looking to draw a spade next, the number of spades in the deck is 13. We drew a heart on the first draw, so the number of hearts left over decreases by 1, but the number of spades is the same as it was initially. However, note that the total number of cards in the deck is now decreased by 1. Whatever heart we drew on the first draw is now no longer in the deck. We can't draw that card. So it's a little less likely we draw a heart. It's a little more likely we would draw a spade on the second draw. So that's 13 out of 51. We multiply these two together and get about 6.4% or so. What's the probability of drawing 2 hearts on 2 draws? So we need heart on the first draw and a heart on the second draw. Well, on the first draw, just like before, there are 13 hearts in the deck. There are 52 cards in the deck, 13 out of 52. And then we have a conditional probability. What's the probability of drawing a heart on the second draw given we drew a heart on the first draw? Well, given that we drew a heart in the first draw, there's one fewer heart left in the deck. So there are only 12 hearts left in the deck. And there's also one fewer card overall left in the deck. So there are only 51 cards. So 13 over 52 times 12 over 51. Where above we had 13 over 52 times 13 over 51. So a little bit less likely to draw two hearts in a row than to draw, say, a heart than a spade, 5.9% versus 6.4%. Right? Drawing a flush, getting 5 of the same suit out of 5 draws is a pretty good poker hand. You know, that how good a poker hand is directly related to how unlikely it is. The less likely it is to get, you know, such a poker hand, a flush or a straight or whatever it may be, 4 of a kind or something, the less likely it is for that to occur, the stronger the poker hand. The less likely poker hands beat the more likely poker hands. That's how they're arranged. And we see that drawing 2 hearts is harder in a sense, or less likely than, say, drawing a heart than a spade. Any questions on any of these so far? Okay, let's look at another problem here. This is an example of a game show. It's probably the world's most boring game show, but here's how it works. Uh, we go up and we roll a 6-sided die. If we roll a 1 or a 2, we go and draw a card from box 1. If we roll a 3 through 6, we draw a card from box 2. Box 1 has 60% good cards and 40% bad cards, so like 60% winning cards and 40% losing cards. Box 2 has 10% and 90% good versus bad cards. We want to find the probability of getting a good card or winning something from this game. So again, instead of, you know, setting up all of my algebra here, which I perfectly could do, it's actually very similar algebra to what we did with the bad widget, looking for a good card. And if you wanted to practice, you could actually go through this same setup up here and make it work for this this good cards and box 1 and 2 and so game. Or we could use a tree diagram. We could use this pictorial representation to help us with the calculations. So we need to decide kind of which event we check first. Do we check which box we go to or which card we draw first? Well, here it's a little more natural. We kind of get sent to the box before we draw a card. So it's a little more clear that we check the box first. Are we going to box 1 or box 2? We go to box 1 if we roll a 1 or a 2 on a fair 6-sided die. So that's 2 out of 6 or 1/3 of the time. And we go to box 2 2/3 of the time, 4 out of 6. Given that we went to box 1, what's the probability of drawing a good card? Box 1 has 60% good cards. So probability that we win the money given that we went to box 1 is 60%. And given that we went to box 2, what's the probability of getting a good card? 10%. And here's again kind of the math written out. And we see we could either take 1/3 times 60% is 20% for the probability of getting a good card and having gone to box 1. And 2/3 times 10% is about 6.7% for the probability of getting a good card and having gone to box 2. And we see we get 26.7%. So again, we could have gone through this kind of algebra. Oh, scroll up a little too far. This algebraic approach. Or we could have stuck with the tree diagram. Either way would work just fine. Okay, so we have this idea of conditional probability. Sometimes we might be interested in computing a conditional probability. So sometimes we're, essentially just given the conditional probability like we are here, or like we were in um, the machines and widgets example. But sometimes we are interested in computing a conditional probability. So what does that look like? Well, to compute a conditional probability, we just rearrange the multiplication rule. So this is our multiplication rule. And if we just divide through by probability of A, then we get probability of B given A equals probability of A and B over probability of A. So we can compute conditional probability this way. So here's kind of an interesting example. So let's say that I want to flip 10 heads in a row with a fair coin. So I start flipping and I'm asking what are the chances that the next sequence of 10 flips, the sequence of the next 10 flips, ends up being all heads. Well, that ends up being 1 over 2 to the 10th. And we were able to find this a couple different ways from past work. Just kind of extrapolating from things like, how many outcomes are there in a roll of one die, a roll of two dice, a roll of three dice, and so on, six or six squared or six cubed, kind of extrapolating from that, or saying that this is like getting heads on flip one and heads on flip two and heads on flip three and so on, independent events. So that's 1/2 times 1/2 times 1/2, 10 times 1 to the 10th over 2 to the 10th is 1 over 2 to the 10th. So either way, we've done this, basically this exact problem before, talking about five heads on five flips. So the probability of getting 10 heads on 10 flips is 1 out of 2 to the 10th, or about 1 in 1,000, about 0.1%. So now the question is, let's say I'm trying to get 10 heads in a row. I start flipping, and I actually successfully flip 6 heads in a row. So flip 1 through flip 6 are already heads. What are the chances of completing my 10 heads? Completing that sequence of 10 heads. So what's the probability of getting a full sequence of 10 heads in a row, given that I've already gotten 6 of those as heads? Well, that's probability of 10 heads in a row and 6 heads in a row over probability of getting 6 heads in a row. In other words, completing my sequence of 10 and already having a sequence of 6. But if I get a sequence of 10 heads in a row, then that automatically means that I have a sequence of 6 heads in a row, right? If flips 1 through 10 are all heads, then certainly flips 1 through 6 are definitely heads. So 10 heads and 6 heads is really just boils down to probability of getting 10 heads. From a Venn diagram perspective, the event getting, say, 6 heads, or in other words, a head on flip 1 through flip 6, compared to getting 10 heads, in other words, heads on flip 1 through flip 10, the 10 heads event is strictly inside of the 6 heads event. So if I satisfy the 10 heads event, I automatically satisfy the 6 heads event. So really, this just boils down to the more restrictive of the two, the probability of getting 10 heads. And then over probability of 6 heads. And that's the details for this first equal sign here, where all of that came from. It looks very strange at first. You say, wait, where did my and go? Well, that's where it went. Getting a head on flip 1 through flip 10 is a more restrictive criterion, strictly more restrictive than getting ahead on flip six. So this bit, while it's kind of there in name, it doesn't practically do anything. Okay, and then what is this? 1 out of 1024 over 1 out of 64, or that's 1/16. That's about 6.25%, or that's 1 over 2 to the fourth. Interestingly, 1 over 2 to the fourth is 1 over 2 to the power 10 minus 6. On this next slide, this is a bit abstract. I'm going to skip over this mainly for time considerations. But interestingly, a problem like this has what we sometimes call a memoryless property. In other words, what's the probability of completing my 10 heads given that I've already completed 6 of those, 6 heads of that sequence? Well, the math, the probabilities couldn't care less about what you did before. They only look forward, right? There's no looking in the rearview mirror. There's a memoryless property. The question of what's the probability of completing my sequence of 10, given that I've already got 6, is the same question as what's the probability that if I just started from scratch, that I flip 4 heads on 4 flips, 1 over 2 to the fourth, right? So we completed 6 and we want to get to 10. We just look forward and say, I need to get 4 more, right? There's no memory of what happened in the past. There's no adjustment for, oh, you got a bunch of heads, maybe tail should be more likely or head should be more likely or any of that. Just says you got 6 in a row, you need 4 more, you know, always looking forward. I feel like there's maybe a little bit of a life lesson there, right? That we, um, yeah, that there's a catchy little phrase that's something like there's a reason that the windshield is much bigger than the rearview mirror or something, right? Like, um, so this is a memoryless property, and these come up, fairly often in statistics, probability and stats. This is the math kind of showing that this works in general. It's not just something specific about 10 flips, 6 flips, and 4 flips and having a 50-50 chance or whatever. Like this is a more general idea. Okay, let's look at a little more applied scenario here. So I did grad school at Pitt, University of Pittsburgh, and in Oakland, parking is always a bit of a nightmare. So let's talk about parking and getting parking tickets. So let's suppose that the probability of parking in a no parking zone and getting a parking ticket is 6%. So, over the last 100 days that I had to drive down to Pitt and go to class, 6 of those days I parked in a no parking zone and got a parking ticket. Now, let's say that the probability that we can't find a space and need to park in a no parking zone is 20%. So of those last 100 days, 6 of them I parked in a no parking zone and got a parking ticket, but 20 of them I parked in a no parking zone. Now the question is, given that you parked in a no parking zone today, find the probability you'll get a ticket. So we're really kind of we're kind of challenging the notion of probability here a little bit. So we're almost thinking about this contextually as like, when I woke up this morning, before I left my house or whatever, I said, okay, I mean, I think that the probability that today I have to park in a parking zone and I get a parking ticket is 6%. But I get in my car, I go and drive down to Oakland, and there's some crazy event going on. There's no parking. I have to park in a no parking zone. Well, have to is a bit strong, right? I don't have to really do anything, but I choose to park in a no parking zone. Well, now that I have this new piece of information that I did park in a no parking zone, I mean, that should update my chance of getting a parking ticket, right? We would think that that would make it more likely to get a parking ticket given the new information that I parked illegally than given no information about how I was going to park today. So I'm guessing that my probability is more than 6% now. It should be. Well, let's check. So probability of, actually, I think I have this on the next slide, probably typed out nicer than what I could write it out here. But the probability of getting a ticket, given that we parked in a parking zone, so given that I have more information, I got to campus and there was nowhere to park, I had to park in a parking zone. What's the updated probability that I get a ticket? It shouldn't just be baseline of 6% anymore. Probably should be higher, right? Just reasonably speaking. But that's probability of getting a ticket and parking in a parking zone over probability of parking in a parking zone. Or that's 6% over 20%, or it's a 30% chance. So when I woke up this morning, I might have thought there's a 6% chance I get a parking ticket today, but I get to campus and I choose to park in a parking zone. And now that chance of getting a ticket today has increased from 6% to 30% on the basis of this new information. Now, in this case, I'm actually speaking more like a Bayesian with subjective probability, where I'm talking about my personal degree of belief in getting a ticket based on the individual experiences that I have, like knowing that I chose to park in a parking zone today. So that's why I say I'm kind of pushing the boundaries of what we ought to be saying this probability represents here. But we are overlaying this on a real world example, so I feel like, it's a bit valid to do that here. And we'll actually talk in a good bit of detail about Bayesian statistics after chapter 5. Okay, I think I'm actually going to skip this last example. It's kind of just an interesting side example, but we are running a bit short on time, and I do want to at least get a good start on this last PowerPoint slide for chapter 4. Are there any questions on those two PowerPoints that we've gotten through already? The basics of probability, the addition rule, and the multiplication rule. All right, just for your reference, I just popped the part 3 PowerPoint in the chat. Did remember to do it in the right order this time. Zoom won't let me like put something in the chat if it's currently open. So I did remember to put it in there before opening it. There we go. Okay, so let's jump into the third PowerPoint. The third and last PowerPoint for chapter 4. This one's a little bit shorter, as in fewer slides, but I think this there's also a pretty high density of information here. So this last part is all about counting. So far, I guess we don't have a really good example here, but in our previous work, we said, well, at least up to what we've done now in chapter 4, we set up a sample space with outcomes that are equally likely. And then we have an event whose probability is just the number of outcomes in the event over the number of outcomes in the sample space. So far, we've considered events and sample spaces where either the number of outcomes is easy for us to just explicitly count, 1, 2, 3, 4, 5, something like that, or where maybe it follows a very simple pattern. Like on one die roll, we have 6 outcomes. On two dice, the roll of 2 dice in sequence, maybe is how I was going to say 2 dice rolls, but that's not the right thing. The roll of 2 dice in sequence, there are 6 times 6 different outcomes for those sequences. For the roll of a sequential rolling of a die 3 times, there are 6 times 6 times 6 or 6 cubed different outcomes and so on. And we said a similar thing for like coin flips, right? So unless it followed a very simple pattern like that, or was able to be explicitly counted just, 1, 2, 3, 4, 5, etc. Um, we haven't really looked at more complicated sample spaces or more complicated events yet. But we can imagine that there might be sample spaces with a ton of different outcomes in them, or events with a bunch of different outcomes in them. I mean, even rolling a die 3 times, we saw that that was going to be a pretty difficult counting problem if we hadn't had the ability to use the complementary event and make the counting problem really simple. We saw that last time. So we would like to build up our ability to count the number of outcomes in certain events or in sample spaces where that counting problem is not trivial. So that's our goal in this section. And all of this works off of the basis of the fundamental counting rule. So suppose that a probability experiment consists of n ordered trials, each of which has k sub I possible distinct outcomes, then the total number of unique sequences of outcomes is n equals k1 times k2 and so on times kn. So just the product of the number of outcomes in, the product of the number of, I used outcomes twice here in 2 different contexts, but the product of the number of outcomes in uh, each of the probability trials. So for one example, how many possible outcomes or unique sequences are there in 4 flips of a coin? So we basically have 4 boxes to fill in. We have kind of 4 individual probability experiments or trials. And each one has 2 distinct possibilities, heads or tails. So my fundamental counting rule says multiply those together, get 2 to the 4th, is 16. If we want to check, we could actually enumerate all of the outcomes. The sample space is this. We can get 4 heads on each flip. We can get 3 heads and a tail, where the tail occurs on the 4th, 3rd, 2nd, or 1st flip. We can get 2 heads or 2 tails, or 2 heads and 2 tails, in any of these 6 ways. We can get 1 head and 3 tails, where the head occurs on the 1st, 2nd, 3rd, or 4th flip. Or we can get all tails. So this, even for, 4 flips of a coin where there's only 2 choices in each box here, this is actually quite a lot of outcomes, right? To write out, especially with the 2 heads and 2 tails. That can be a little tricky to get all of them and not repeat any of them and not miss any of them. So another question we might ask is something like, how many standard Pennsylvania license plates are there? So a standard PA license plate looks like 3 letters, and then there's the little keystone bit, and then 4 numbers. Now, it is important that the letters can be chosen with replacement, right? So, oops. So ABC 1, 2, 3, 4 is a valid license plate, but also AAA 2222 is a valid license plate. It's not like if I use a letter, I can't use it again, or if I use a number, I can't use it again. So we're not like in the card drawing scenario for like a poker hand. We're kind of drawing with replacement. I pick out a letter, I look at it, write it down, and then put it back in the bag, and I can pick it again. Note also that the ordering matters. The plate ABC 1, 2, 3, 4 is a different plate from CBA 4, 3, 2, 1. Even though, like, maybe a poker hand, if I drew, 2, 3, 4, 5, 6 in that order, say all of hearts, that's the same poker hand as if I drew 6, 5, 4, 3, 2 in hearts, or 2, 5, 4, 3, 6 in hearts, right? Those are all the same poker hands. So in that case, the ordering doesn't really matter, but in license plates it does. ABC 1, 2, 3, 4 is a different license plate than, say, CBA 1, 2, 3, 4. Well, what's the number of distinct license plates? It's going to be, well, 26 choices for each of the first 3 letters. and then 10, 0 through 9, 10 choices for each of the four numbers. Or that's 26 cubed times 10 to the fourth. And if we go over to our calculator, well, came up on the wrong screen. We go over to our calculator. We have 26. I use my caret symbol here above the divided by sign to the third power, and then times 10 to the fourth, which is a 1 with 4 zeros after it. Right, so I have 3 zeros, and then 760, and then 175. So that's 176 or so million different possible plates. Yeah, there's like on the ballpark of like, 10-ish million people in Pennsylvania. So that's probably more than enough plates for the number of people in Pennsylvania. And of course, we have, custom plates and all kinds of other different plates too, but 176 million or so plates for the people in Pennsylvania. So here's an interesting question for kind of the IT folks. Um, let's think about passwords. How many passwords are there consisting of 8 lowercase letters? So you have a password, and I need to choose 8 lowercase letters. For each letter, there are 26 different choices. And of course, the answer is 26 to the 8th. So 26, caret symbol 8. 26 to the 8th power is about 2 times 10 to the 11th. Be really careful. When we have a kind of big number, oftentimes the TI will put it in this format and just write the number out with a bunch of digits. Depending on where your mode is set, if you have your mode set to float here, see where it says normal, and then if you go down one, there's float. That'll usually write out like 9-ish digits. I think it's 9 of them. But you can also actually tell it the number of digits you want it to write out. But once we get too many digits or we surpass whatever you have it set to, it starts reporting the numbers in scientific notation. So we have to be really careful here. We don't want to look at this and think, oh, the answer is 2.08 or 2.09 or whatever. Well, of course, that's not the answer, right? There's not like 2 passwords. There's a bunch of passwords. Well, we have 2.08 or 2.09, E11. Well, that means 2.088 times 10 to the power or to the exponent 11. So this E11 is actually probably the most important part of this number. We have to be really careful that we check for that. We know this is going to be a big number, so we know it's not going to be, 2 passwords. And we also know that should be a discrete answer. Should be a number like 4 or 5, 6. It should be a whole number answer. So getting a number like 2.09 or something wouldn't make sense anyway. So we could ask the question now, okay, we want to make our password a little more secure. How many passwords are there consisting of 8 characters? But they can be lowercase or uppercase letters. They can be numbers or any of 10 special characters. Oh, I'm not being careful. I scroll down when I'm not hovering over one node and I'm hovering over PowerPoint, and it does that. I feel like I've done it a couple of times today. So now instead of 26 lowercase letters, I have 26 lowercase letters, 26 uppercase letters, which we take to be different characters, 10 numbers, and 10 special characters. So I have 52 plus 20 is 72. I know 72 distinct characters that could go in each of these boxes, but I still have 8 boxes. If I do 72 to the power 8, I see I get 7 times 10 to the 14th. I only have, something in the ballpark of like 1,000, 10 to the third times as many passwords by, increasing the complexity this much. It's a little bit of a silly thing to do, actually, right? This is a ton of increase in complexity, makes it really hard for people to remember their password. But I only get 1,000 more passwords, or not 1,000 more, 1,000 times as many passwords. I only get 3 orders of magnitude boost here. Now, there is another reason that they do this, and that's encouraging people to like not use like password as their password or something silly like that, right? Which can be subject to different types of attacks that aren't just brute force. So there are other considerations here, like all of our models were, using simplified versions of real life problems to illustrate certain concepts. Um, so there are other considerations to be taken into account here. But we could also ask, well, how many passwords are there consisting of just 10 lowercase letters? So one way that I could increase the number of possible passwords, making it harder for somebody to just brute force their way into my account, is by increasing the number of possible characters or the number of possibilities for each character. Another way is by adding more characters on, by having a longer password. If I add just 2 characters on, but keep 26 options per character, 26 lowercase letters, the number of passwords is 26 to the 10th or 1 times 10 to the 14th. The same order of magnitude as this big complicated green one with all of the capitals and lowercase letters and numbers and 10 special characters. So there's a sense in which making your password longer is higher yield. You get more bang for your buck than, having all these different kinds of, upper and lowercase letters and numbers and special characters and so on. And why is that? Well, that's because if we start with, say, 26 to the 8th, we can either increase the base to, what was it, 72, or we can increase the exponent to 10. Increasing the exponent corresponds to exponential growth, which grows much, much faster than polynomial growth, which is increasing the base. Now, like I said, there are things like dictionary attacks and things that if you're interested, you can look them up. So there are other considerations here. But these days you're seeing security folks go more towards the use of passphrases where it's like they want you to have a 14-character password or something, and they're less worried about whether it has special characters and all kinds of crazy stuff in it. Okay, so let's end on this example. I think this is just a really cool one, cool example to think about. But so if we think of the human genome, our, you know, contents of which are in every cell in our body, almost not every cell, almost every cell. And yes, like red cells and things don't have the human genome in it, but in most cells of our body. So we can ask how many different genetic sequences are there for, say, a human genome? Not how many different actual people have, this sequence, but in theory, how many different sequences are there? Well, the human genome has about 3 times 10 to the ninth base pairs, about 3 billion base pairs. So I think this is, pretty common, like high school level science. I'm not 100% sure though, so I don't teach science, but our genetic material, it's in a helix shape and it's, wound around a bunch of different ways, but most basically, it's just kind of a ladder structure. If you unwind it in all of the different ways it's wound around and kind of stretch it out and were to lay it flat, you would see that you have 2 sides and it just looks like a ladder. And each one of these little pieces on one side of the ladder is called a nucleotide. And it's either A, C, T, or G for the 4 nucleotide bases. So is adenosine, cytosine, thymine, and guanine. And they hook together. A always hooks with T, and C always hooks to G. So basically, if I know that this is an A, roughly speaking, unless something has gone wrong, which does happen, but then this should be a T. If I knew that this was a C, this is a G. So really, I need to know one side of this. And then that's all of the information, again, roughly speaking. And there's about 3 billion. This list is about 3 billion nucleotides long. Well, if we were to just combine, take chromosome 1, lay it out, and then stick chromosome 2 at the end and lay it out and do that for all the chromosomes. So what's the number of human genomes? Well, I have a bunch of little boxes that have 4 choices, A, C, T, or G. How many of these boxes do I have? 3 billion. The number of human genomes is 4 to the power 3 billion. Or that's like 10 to the 1 billion roughly. 4 cubed. I mean, 4 cubed is 64, but it's like on the order of magnitude of 10. So that's like a 1 with like a billion zeros after it. Or it turns out that if you think about how many gigabytes of data is this, it's like a 1 to 2 gigabytes of data. Like if we wanted to store just, if we said like A is 1, 1, C is 0, 0, T is 0, 1, and G is 1, 0, and we just wanted to list them out in binary, it would take like more than a gigabyte to list that out. And that's that amount of data stored in every one of our cells in our body. I don't know. I think that's kind of crazy. It's like if I, swipe my arm or something and a bunch of dead skin cells fall off, like that's probably as much data storage as is on the hard drive of my computer. I don't know. I think that's just really cool. But there are an unfathomably large number of, possible human genomes. Now, of course, the vast majority of the genomes are not compatible with life or would not make a human or anything that resembles a human or whatever. Um, but that's the amount of data that's stored in our genomic data in the nucleus of, roughly speaking, every cell. Don't tell your biology professor that I said every cell, but more or less. Okay, so that is all for today.